Yes, okay, that's working. Okay, so where we left off last time, we're starting to multiply radicals, and when we're multiplying radicals that involve binomials that have radicals, then we're also starting to mix up the properties of adding and subtracting as well, because first we multiply, but then we have to see if we can combine any like terms before we walk away. So all these rules are getting worked up together. Okay? So a little crossover from the addition into the multiplication is keeping in mind these basics. For example, if you had 2 square root of 5 plus 7 square root of 5, or if you had the same terms, 2 square root of 5 times 7 square root of 5. You want to be very, very cautious and aware of when you see a problem you're supposed to simplify, of being very aware. Your first thing your brain should go to is what's the operation. Because that changes everything. The rules are different for addition as they are for multiplication. In this case, can we add these? What do we need in order to add them? Yeah. Okay, and in this case, no, we don't call it bases. That would be the term for exponents, but in this case, the same radicand and the same index. So these are like radicals, because they're the same index and the same radicand. This would be like saying now 2x plus 7x. Because the square root of 5 is exactly the same. That's like having the same base and the same exponent. Okay, like term, like radical. So that means that what is our simplification? We combine the numerators, we combine the coefficients and get what? But it's still the square root of 5. Right. Because just like 2x plus 7x is 9x, x is still the same, apples and apples, it's still apples. The square root of 5 doesn't change. Now here, this is all multiplication. This means 2 times square root of 5 times 7 times square root of 5. Are we allowed to multiply these? Yeah. By the product rule, as long as we have the same index, doesn't matter about the right. Now it happens these radicands match, but it doesn't matter if they did or not. As long as we have the same index, we can put 2 radicands under the same house. Okay? Now understand that all of this is multiplication, even though we don't write the dots there. That's 2 times square root of 5 times 7 times square root of 5. So the first thing you want to do in simplifying this is deal with the outside numbers. Okay? So this has a coefficient of 2 and a coefficient of 7. What's our new coefficient? Right, multiplying it. Here we added them, but kept the same radical. Here we multiply them, but what's our new radical? Right, it's square root of 5 squared. Now there's a couple ways to write that. We can, by the product rule, we can combine them under one house. Well, that means we got twins, so 5 is the root, or if you make this square root of 25, that is 5. Okay. Another way to write it is 14 and then square root of 5 squared. Okay. Or 14 square root of 5 squared. Okay. 5 times 5 under one house by the product rule is 5 squared, square root of 5 squared. Or square root of 5 times square root of 5 is square root of 5 times itself, or square root of 5 squared. Either way, the exponent cancels out the index. The exponent cancels out the index, whether it's underneath or whether it's on the outside. And that obliterates the radical sign. Okay? Multiplying a radical times itself kills the radical sign. That allows you to root and release it. Okay? And so this equals 14 times what? Times 5, right? Which is 70. Okay. Okay. About 3 square root of 2 minus 8 square root of 3, or 3 square root of 2 times 8 square root of 3. Same terms, but this operation is subtraction and that one's multiplication. Okay. So what would this be when we subtract them? Yeah, can't, right? This is like 3x minus 8y. Okay. Unlike radicals. Okay. Same index, but not the same radicand. They have to have both the same index and the same radicand. So there's nothing wrong with this. It's not, don't say undefined or no solution, those words don't apply. It's just done. I mean, you can't simplify. It's perfectly fine. It's just already as simple as it gets. Here with multiplication, that means we have multiplication all the way across. 3 times square root of 2 times 8 times square root of 3. So what's the first thing we write down? 24. Deal with our outside numbers, 3 times 8. Our new coefficient, because we can change the order of multiplication as 3 times 8 times square root of 2 times square root of 3. 3 times 8. You can only multiply non-radicals with non-radicals and radicals with radicals. Okay, you can't smoosh together a radical and a non-radical. So we take care of the coefficient first. And then, do we lose our radical sign? No. I mean, here we did, because a radical times itself obliterates that radical sign and becomes just the radicand. But here, we still have our product rule. We can put them under one house, but if they're not twins, it doesn't kill the radical. Okay? So we're not squaring anything. So if we're not squaring something because these aren't the same, then that means it doesn't cancel out the index of square root. Okay? So there's still a radical sign. You have 24 square root of 6. Okay. Now, if then you look at that and think, is that a perfect square, or is it contain a perfect square? I can simplify it, either simplify it or partially simplify it, then you would before you move on. If anything could be squared out of it and pulled out to multiply times the coefficient, great. In this case, no. 6 is done. Okay with that? Okay. So looking at the handout, the handwritten one. Oh, and on the back side, just say, somebody, and I apologize if it was you, and I forget who did it, just when we were down the lab, was Googling. So if you find this useful, this is just a table of perfect squares, cubes, and fourths and fifths. Sort of as a study table, like having your multiplication facts. So if you find it useful, there's a copy for you. Right. Now, of course, you see how big these get, how fast these get really big. It's not a matter of memorizing these. I generally think if you have the first 15 perfect squares and the first 10 perfect cubes and the first 5 perfect fourths, even the first 3 perfect fifths, just knowing those, okay, just the 3-digit ones basically, is useful to have memorized, to recognize. After that, it's all calculator. Okay. Now, the other one, the handwritten one, these are basic multiplying radical rules. Okay. So, we've got a basic product rule, and I included the ends here because it could be any index. It doesn't matter what the index is as long as it matches. So you've got 2 different radicands, and the product rule, not addition, product rule allows us to multiply them under one radical sign. Okay. And then simplify if possible. In this rule, I didn't include the ends because this is specifically for square root. Okay? If you multiply something times itself, you're squaring it. Okay? If you had a cube root here, then you'd have to do it times itself 3 times. Square root of a, sorry, cube root of a times cube root of a times cube root of a. Or if it's the fourth root of a times fourth root of a 4 times. Okay? So really, just for this rule, we're just focusing on the squares. Okay? So if you've got a square root of something times itself, that can be written as one of these 2 ways, the square root of a squared or the square root of a squared. Either way, the square and the index cancel each other out, kill the radical, and releases the radicand. Okay. 2 very important rules moving forward with all the multiplication and simplification we're about to do. Now I just added in the corner here in my earlier class, and you can write this down. I'm also going to scan and post this. But just to contrast the adding radicals, the rule for that is that you need like radicals, as we were just discussing. That includes same index, same radicand. Just summarizes what we were talking about last time. And for example, very different cases here. Square root of a plus square root of a. Square root of a times square root of a is just a. Square root of a plus square root of a, like radicals, combine the coefficients. 1 plus 1 is 2. It's still square root of a. Square root of a plus square root of b, different radicands, are not like radicals, and therefore nothing you can do. This is kind of a summary of the adding rules. Okay. So, like I said, I'll scan this in and also leave this out if you want to take a picture of it. Okay, so it just summarizes what we did last time. You can add it to the sheet. But let's look ahead at the special products. Okay, so don't worry if you're scribbling really fast. You'll get an opportunity to finish that up. Okay, so we're jumping into special products now. This is kind of where we started last time. We started with distributing. So multiplying radicals, including distributing, which is where we left off last time, okay, involves, you already know how to distribute. Okay? It's like you know these special products as well. You know how to do this. We're just doing it with some radical terms now too. So you have to understand how the radical properties work, but the skill itself is not different. Okay? So when you distribute, you multiply an outside term times 2 or more inside terms, and then each one gets simplified and you combine like terms if there are any. Okay? So you just have to know how to simplify and combine radicals, but the act of distribution is the same. Okay? And then so we'll start with the distribution one, and then we'll also look at further at all these other special products. 3 basic special products. Now a lot of these with regular terms, non-radicals, a lot of these you're starting to do even more mentally. Okay? Great. Hopefully they're becoming very, very routine. Okay? When you FOIL, no problem. You just know how to FOIL. Okay? Binomial squared and conjugates. I know some people resist at first. I'm really pushing these patterns for a reason. Okay? But we'll get to that in a sec. So FOILing, basically, while you may go directly mentally with regular terms, you know, you go, first terms, and then your O and your I, and a lot of times you can add your O plus your I, and you put that down, and then your L, your last term. Okay? When we're doing it with radicals, I strongly recommend writing out the expanded step first, especially with FOILing. FOILing with radicals gets really messy and chaotic looking. If you take the time just to write that first expanded step, it really simplifies things. Okay? But basically, FOIL is first terms, outside terms, inside terms, last terms. With radicals or not, it's all the same pattern. Okay? Then you use your radical rules to simplify each little package, and the radicals of multiplication to simplify each little package, and radical rules from addition to see if you can combine any like terms. Now, binomial squared, make a pattern. When I give you binomial squared with radicals in it on the test, if you expand it out to a plus b times a plus b, and you FOIL it, and you get the right answer, then you will get credit for that, but not full credit. Okay? What I want you to show me is not just the right answer, but that you are working with the pattern. Okay? I'm a real stickler about that, because it's going to help you moving forward. This is not going away. Okay? So, the binomial squared, don't think of it as memorizing a formula. Think of it as mental FOILing. You've got this binomial times itself. So your first term is a times a. That's your first term squared. Your outside is ab and your inside is ab. And because this is a binomial squared, it's 2 pluses. So it's positive ab plus positive ab. Those are like terms. It's just ab doubled. And then your L's, b times b, is b squared. Now, if your middle term is positive or negative, then that's going to make the middle term either positive or negative, doubled or negative doubled. Because you either have AB plus AB, AB doubled, or you have negative AB plus negative AB, negative AB doubled. But for the last term in L, B times B, 2 pluses make A, and 2 negatives make A. So regardless, the binomial squared is either 2 pluses or 2 minuses, your B squared is always going to be positive. Okay? And again, no doubts, I pointed out before, and I'll keep pointing out in new context. Binomial squared have a middle term. Okay? That middle term, that O and the I are the same. Either AB and AB or negative AB and negative AB, they're the same, so it's just the middle term is just your AB doubled. Or negative double is a minus. Okay? So when I wrote this out, I also noticed how I put the A's and B's in parentheses. That's going to be important moving forward too. Okay? And I'll put that as we do examples. I'll say why I'm doing it that way, to be really clear about our exponent rules and how we deal with radicals. Okay? Now, conjugates, our other special product, that's when we have the same A's and B's, like here, but one's positive, one's negative. Now, if you FOIL that out, if I give you conjugates and say multiply and you FOIL it out, you will get it right, you will get partial credit. Okay? What I want you to recognize is the pattern. These are conjugates. Recognize you have conjugates. And a conjugate, if you FOIL this out, you know that the AB and negative AB, your O and your I, are opposites and they cancel out. There's no middle term, with the difference of squares that you get from multiplying conjugates. Conjugates multiplied have no middle term because the O and the I are opposites, and so it cancels out. And the results in a difference of squares. You still have this perfect square A and the perfect square B on the front and the back end, but because the signs are the same here, your middle term is 2AB, or negative 2AB, and here your middle term is canceled out and doesn't exist. Okay. So if you recognize you have conjugates, rather than FOILing out and getting partial credit, put it in the pattern. Square the first term, understand the middle term's disappeared, and square the last term, but because it's mixed signs, it has to be subtraction. Okay. Difference of squares. Okay. Okay? Okay. So we're going to put all that practice with actual numbers and radicals now. This can be a good reference sheet while you're practicing, and understand I am emphasizing using these patterns, and I'm doing that for a reason. Okay? Maybe you'll thank me later, I don't know. But keep that as a reference for now. You don't get to use this on the test, but you keep it with your homework and understand that that's the kind of, that's what you want to absorb and become natural. Don't fight those patterns, those formulas. Okay. Okay, so the second half of 11.4 is multiplying. But before we do that, there's actually a couple of problems we didn't get to do an example of about adding that you may have come to in homework. So let's look at those first. So we'll start off with just a couple of adding, and then we'll transition back into multiplying with all of our special products. So adding radicals, the first part of 11.4. In this case, you're adding radical terms. You have to have like radicals, but you don't know if you have like radicals until everything is simplified. Okay? So you have some radicals added to each other, make sure all the radicals are totally simplified. Either they're perfect squares and get released, or they're partially perfect squares and can be partially released, and then any like radicals can be combined together. Another variation of this involves fraction form. Okay? So here, for example, you have 2 square root of 2 over 3 plus 3 square root of 2 over 5. Okay? So you're going to see a couple examples like this on the homework. And it's the same rules for adding radicals as we had before, but it also involves rules for adding fractions. To add fractions, what must you have?
Same denominator.
Exactly, common denominator. So that's your first goal. Once you have a common denominator, you're going to add the numerators. Okay, so you're going to worry about that in a second. First, you got to put these numerators together over a common denominator. Then you'll look at your rules for radicals to combine the numerator. First, you deal with your rules for fractions. Now we just came out of Unit 2 we're dealing with rationals, finding common denominators for polynomials. So hopefully going back to just working with common denominators for fractions is like, oh, fractions aren't so bad now, because those polynomials got big and ugly. But it's the same mathematical rules. A common denominator, the denominators must match, and to make it match, you multiply something on the bottom to make a match, and whatever you do on the bottom, do it on the top. That's a legal move, and then you're good to go. So here, our common denominator should be 15, right. It's always your biggest one or bigger. 5 doesn't work, so we count by 5s. 10, no. 15, check. Now, how would we turn 3 into 15? Right. And that is a totally legal move as long as we do the same thing on top. Because any number over itself equals 1, so basically we're multiplying this term by 1, which means we didn't change its identity, didn't change its value. Legal move. And I multiply it in front, notice, because it is a number, not a radical. Okay? So if we put it on the back and made the square root of 10, that would just be totally off. Okay? We're multiplying times 5, so it goes in front with the other free number. How will we make this one into 15? So be fair to the top. Okay. Now our common denominator, now we write one rational bar, and our common denominator is 15, and that doesn't change. It doesn't become 30 or 225. We don't multiply or add the denominator. The common denominator is 15, and that's what it is. Because we have the common denominator, now we can combine our numerators on top. So we've got 10 is our new coefficient, square root of 2, plus 9, square root of 2. Make sense? Stop me if that was a... Now that common denominator is what it is. It's done, but now, if possible, we've taken care of our fraction rule with the common denominator. Now we use our radical rules to see how we can simplify this numerator. So these are all, the square root of 2, that's as simple as it gets. So we say, can we add these two things together? Yeah. It's addition of like radicals. Both square roots, same radicand. So we just combine the numerators. So what's our new numerator? We combine the coefficients. What's our new numerator?
19. 19 square root of 2 over 15.
Right.
Would it be... I guess. I'll just say, would it be illegal to simplify the 10 and the 15, but it's touching the radix, so you can't do that?
Right, the 10, oh, here, oh.
Yeah.
Only if you simplify it here and here. So this 15 belongs to both of them. So you could simplify this as 2/3. You could simplify this as 3/5.
Yeah,
but then you go back to where you started. Yeah, yeah. Don't reverse the work you just did. Yeah. So that would be a legal move if you're fair, but then it doesn't get you where you want to go. Yeah. Now at this point, once you combine them, check and see if you can simplify that before you walk away. And you can't, but you would if you could. Never, ever, ever, ever. Let's say this was a 16 on the bottom. Could you simplify the 2 and the 16? Radical, non-radical. Not friends. Do not interact. This is not actually a 2. Square root of 2 is a totally different value. Put it in your calculator and you'll see. And it's 1 point something, irrational number. Okay? This is not a 2, so it cannot interact with this number. Okay? Even if your eye says, oh, I can reduce that, 2 over 16 if it were, nope, not allowed. Okay? Now, if you can, before you find a common denominator, if you can, or if you must, I'll show you in this case, both cases, you must simplify everything first. Okay? And then you find a common denominator, and then you combine your numerators. So in this case, there's nothing to simplify first, just got your common denominators, combined your numerators. Here, this one involves a variable as well, 2x square root of 11 over 5 plus square root, big square root, of 11x squared over 100. Now here we have a 3 and a 5 for our denominator, so we can go ahead and find our common denominator of 15. So do we here need to find a common denominator for 5 and 100?
Not yet.
No, because that's not 100. Okay? It's under a radical. And it's not even under its own radical, it's part of a quotient, part of a fraction that's under a radical. Okay? So we got to start breaking down and simplifying first before we can deal with our common denominators. We have to have 2 free numbers before we can give common denominators. Now what's the first step for starting to break this down?
The square root over 11x squared
Mm-hmm.
and square root over 100.
Exactly, it's the quotient rule of radicals. Now if this were all just one perfect square, we could just go ahead and square root the whole thing. Square root the numerator, square root the denominator, it's free. But this is not a perfect square here. So we have leftover bits, so we have to use our quotient rule first. Just like if I had just given you this and said simplify, this is from the last class, and is break it up into 2. So we'll just drag this along, 2x square root of 11 over 5 plus square root of 11x squared over square root of 100. Now, my next step can be the expanded step, and as long as you do the expanded step, do that as long as you keep things clear. But for smaller ones like this, I might start finding some mental shortcuts as appropriate. That's what homework is for figuring out what strategies work for you, what do you need to write out, where can you do mental steps. So I look here, this is a perfect square, that'll take care of itself, but the top, it's not a perfect square, right? It has 2 elements. Is either of them a perfect square?
Yes.
You got 11, you got x squared. Which one's a perfect square? X squared. So what I would do, I'd like to, you get to the point where these smaller ones you can do more automatically. But just to be clear on if you want to write it out in expanded form, that's great, go off to the side. Don't try and clutter it up here. Okay, that's going to just ask for careless mistakes, chaos. Okay? So if I have something I want to simplify and I don't want to do it mentally, I want to make sure I write it out and I'm really clear, then my regular old form, this is square root, I put the perfect squares on the left and the leftover bits on the right. By my product rule, I can separate them. And I root and release the left, and that stays locked up on the right. Okay? So that becomes square root of x squared is x. Yeah. Square root of any perfect square is just the base. And then square root of 11 is my leftover bit. It stays locked up. I was able to square root the x squared, but the 11 stayed trapped behind. So the more you can start to do those kind of mentally, great. But if you're not there yet, that's fine. It's no harm. Just go off to the side and do your pencil and paper work so you keep your workspace uncluttered. 2x square root of 11 over 5 plus x square root of 11 over 10. Now we've got nice free denominators, and we cleaned up the numerators, as well. Get that done. We could have done that later, but it's easier to clean everything up at once. So our common denominator is 10. Yeah, it's either the biggest one or bigger. The big one works in this case. We only have to change this one times 2, and on the front here times 2. Now that gives us 4x. 2 times 2 times x. Our new coefficient is 4x, square root of 11, plus x, square root of 11, all over the common denominator of 10. As you see, unlike this one involves some variables. So you've got some more rules of, first, are these like radicals? Yeah, so you're going to be able to add the coefficients. Huh? But now we look at the coefficients. In this case, our coefficients were just numbers. Those are like terms. You not only have to have like radicals, but to combine your coefficients, you have to have like terms for your coefficients too. Here our coefficients are like terms, 10 and 9, add to 19. Here we've got variables involved, so yes, these are like radicals, so we can combine our coefficients if our coefficients are also like terms. 4x and x, are those like terms? Yeah, both simple x's, no exponents. And so 4x plus x is? No. And then keep the same radical, of course. Okay. Over 10. Ready to walk away? Yeah. Okay. One last thing. Yeah. That 5 and 10 is like simplifying to 1/2. Okay. Leaving a 1x, or just an x, square root of 11 on top, and a 2 on the bottom. As I keep pointing out, most of these individual rules are pretty simple. Understanding like terms, like understanding, like radicals, when you can add. Each individual rule is basic, but look at all the rules we're starting to mix up in one problem. Okay, so that's keeping those rules clear and organized, and not panicking. Everything I'm showing you, you already know how to do. You just have to recall that you know it, and get very clear and organized as you practice in your homework about the steps and the order you go in. Okay. Any questions on this? Okay. Right. So let's continue in 11.4 and pick up where we left off with multiplication, specifically distribution. So we showed an example or two of that last time. So we'll start with one example there and then move into our other special products. Okay. So distribution, for example, square root of 7 is on the outside of this binomial that contains square root of 11 plus square root of 7. So we've got distributing a term over a binomial, and at least one of our terms has a radical, in this case all of them. But if at least one of them does, then when we distribute, we already know how to distribute, but don't skip the expanded step when you have radicals involved. So instead of trying to do this mentally, I'm going to write it out as square root of 7 times square root of 11. You can use a dot or you can put them in parentheses. Either one means multiplication. I'm multiplying this times this. Sometimes I use a dot, sometimes I use parentheses. Now, the next thing I put is either a plus or a minus. I always